Watch this carefully. The mug falls, it shatters. Now I want you to imagine something. Sit down next to those broken pieces. Just wait. Wait for them to spontaneously leap off the floor. Wait for every fragment, every microscopic shard to fly through the air in perfect reverse coordination and reassemble into a perfect mug in your hand. You could wait there forever. That simple question leads us to one of the deepest mysteries in physics. Because according to every fundamental law we've discovered, there is absolutely nothing preventing those fragments from reassembling. The atoms could do it. The forces allow it. The mathematics permits it, so why doesn't it happen? Today we're going to find out. The world is filled with irreversible phenomena. Waves crash onto the shore, foam spreading across the sand. Have you ever seen foam collect itself, rise up from the beach, and fall back into the ocean as a perfect wave traveling backwards? Ice melts but doesn't spontaneously freeze. Smoke disperses but doesn't reconcentrate. Eggs scramble but never unscramble. Film these events and play them backwards, and everyone laughs because we know that's not how reality works. But this laughter reveals something profound. It reveals that the difference between past and future isn't just philosophical. Think about how differently you experience the past versus the future. You remember yesterday. You don't remember tomorrow. These aren't just semantic differences. They represent a fundamental asymmetry in reality itself. Time has a direction, and we are made of atoms, and atoms follow physical laws. You'd naturally expect those laws to have built-in directionality, but we haven't found it. In fact, we've found exactly the opposite. Let's examine gravity, one of nature's fundamental forces. Imagine Earth orbiting the Sun. Film it for a year. What do you see? Earth still orbits in a perfect ellipse. A physicist watching couldn't tell if the film was running forward or backward. Gravitational motion is completely time-symmetric. Here's the mathematical truth. If you took any gravitational system and suddenly reversed every particle's velocity, the entire system would perfectly retrace its steps. The same holds for electromagnetism. Time-reversible. Nuclear forces? Time-reversible. Every fundamental force we've discovered operates symmetrically in time. The equations work equally well forward and backward. Yet here I am, speaking to you. My voice travels outward into the air. Sound waves spread and dissipate. They don't spontaneously converge back into my mouth. This is irreversible behavior emerging from reversible laws. Consider friction. Push a heavy block across the floor. It slides, then stops. Friction appears irreversible. But friction is just countless atomic collisions. And each individual collision, perfectly reversible. Remove the barrier carefully. The blue gradually spreads. Within minutes, you have uniformly light blue water. Now wait. Wait hours, days, years. The mixed water never spontaneously separates back into blue on one side, clear on the other. Never. But let's zoom in. Let's watch what's actually happening at the molecular scale. You see water molecules bouncing around in thermal motion. Constant random jiggling. Some carry ink molecules, others don't. As they bounce randomly, naturally, inevitably, they spread out. That's why mixing happens. Now select one collision. Two molecules approach, collide, bounce away at new angles. Play this collision in reverse. A physicist examining this reversed collision would find nothing wrong. It obeys all the laws of molecular dynamics perfectly. The collision is reversible. Every single collision. Reversible. Yet the overall process of mixing, irreversible. Here's the profound insight. The irreversibility doesn't come from the laws of physics, it comes from probability. Think about it. If you start with a separated system and let molecules bounce around randomly, they'll spread out. That's just what random motion does. Consider the actual numbers. A glass of water contains roughly 10 to the 24th molecules. That's a trillion. The probability isn't zero, it's just unfathomably small. This is why your broken mug won't reassemble. Not because physics forbids it. In the 1870s, physicist Ludwig Boltzmann formalized this insight with a concept called entropy. Entropy measures disorder, but more precisely, it measures the number of ways a system can be arranged at the microscopic level while maintaining the same macroscopic appearance. A broken mug has extraordinarily high entropy because there are countless ways to arrange the fragments while still having a broken mug. Boltzmann's revolutionary insight: systems naturally evolve towards states with higher entropy simply because high-entropy states are overwhelmingly more probable. This is the second law of thermodynamics. In any isolated system, entropy never decreases. It either increases or stays the same. The universe contains a fixed amount of energy. It's conserved. Yet we worry about energy crises. Because what matters isn't energy quantity, it's energy quality. Useful energy is organized, concentrated, low entropy. But when we use energy, we inevitably convert it to less useful forms. Heat dissipates into the environment. The energy still exists, but it's now spread out, disordered, high entropy. We can't use it anymore. The ocean contains enormous thermal energy, countless molecules vibrating, moving, carrying kinetic energy. The next towel is wetter. It doesn't help. In fact, it makes you wetter. No matter how many damp towels you have, you can't get drier because there's no difference in wetness between you and them. You're stuck. Temperature is like dampness in this analogy. When everything reaches the same temperature, energy becomes useless. This is thermal equilibrium, the heat death of the universe. The universe is slowly running down, approaching maximum entropy, where no useful energy remains and nothing interesting can happen anymore. If entropy always increases, if the universe naturally flows from order to disorder, how did it get ordered in the first place? We live in a universe with structure. All of these represent low entropy configurations. If you see a partially mixed tank of water, blue fading to clear, and you know it's been sitting undisturbed, you can confidently infer the past. We do this constantly. Geologists look at rock layers and infer ancient environments. Astronomers observe distant galaxies and reconstruct cosmic history. All of these predictions work because they assume the past had lower entropy than the present. The evidence is overwhelming. The universe began in an extraordinarily low entropy state. The Big Bang wasn't just the beginning of space and time. It was the beginning of the arrow of time itself. The early universe was incredibly smooth, homogeneous, organized. And ever since, entropy has been increasing. The universe has been winding down. This isn't a law of physics in the usual sense. The fundamental equations don't care about time direction, but the initial conditions do. This boundary condition, this fact about how the universe started, creates the arrow of time. Why did the universe begin with such low entropy? We don't know. This is perhaps the deepest mystery in cosmology. This asymmetry is why you exist. Why you have memories, why you experience cause and effect, why you age. The arrow of time isn't just a cosmic phenomenon. It's the foundation of your subjective experience. So here's your answer. The broken mug won't reassemble not because the laws of physics forbid it. It won't happen because there are vastly more ways to be broken than to be whole. The arrow of time isn't written in the fundamental equations. It's written in the initial conditions of the universe itself. Every moment you experience, every memory you form, every choice you make, all of it flows from this mysterious asymmetry. Time's arrow flies in only one direction, and the universe is running down.